students, welcome to Sunil's tutorial. I'm Sunil Nirvani and today we'll be doing this chapter called as interference. Let's see the measurement of the distance between the two slits in a biprism experiment. Right? Now in order to find out the distance between the two slits in a biprism experiment, we use the convex lens. So you have to have convex lens in two positions. Initially you keep the convex lens close to the eyepiece. So you would have rays that will move from the biprism. Would get refracted. And hence an image would be formed. Right, this is AB, right, rays of light move this way, and I would have D1, that would be, this distance is D1, which would be my image of A1 and B1, right. Let's call this distance to be X, that is the distance between the biprism and the convex lens to be X, and the distance between the convex lens and the eyepiece to be Y. Right? Repeat the same experiment, but now take the convex lens close to the biprism. I'm going to repeat the same experiment. Here you are getting a diminished image, a real inverted and diminished image. Let's repeat the same experiment, but only this time I'm going to take the convex lens close to the biprism. Right, it gets refracted, the rays of light get refracted, so you would have an image here. This is your distance D, the distance between the two slits of the biprism. This is AB, this distance is D. Rays of light are going to move in this direction, right. This is going to be the image A2, B2, where this distance I'm going to call this as D2. Let's assume that this distance is Y and this distance is X. Right? In order to find out the distance between the two slits in the biprism, this is the experiment that is performed. Yeah.
Yes. So the first diagram, distance between AB and A dash B dash is the same.
Distance between AB, no. You are getting a diminished image. Here you are getting a diminished image. Here you are getting a magnified image. In the first case, you get a real inverted and diminished image. In the second case, you get a real inverted and magnified image. Right? Let's just write the experiment down before we see the calculations. Now, measurement of D, that is the distance between the two coherent sources. Right? So, experiment. First thing that you do is a convex lens is mounted. A convex lens is mounted on an adjustable stand. A convex lens is mounted on an adjustable stand such that the distance between them, between the adjustable stand and placed, such that adjustable stand and placed between the biprism and eyepiece. Right, the first thing that you need is a convex lens. Now you have to do the experiment twice. First, the eyepiece is moved away from the slit the eyepiece is moved away from the slit such that the distance between them is more than 4 times the focal length of the convex lens. That's the initial distance between the eyepiece and the slit, right? Now, the eyepiece is the convex lens is now moved towards the eyepiece. The convex lens is moved towards the eyepiece, right? Is moved towards the eyepiece such that you get two sharp diminished images, such that two sharp diminished images of the slit are seen. Fine. Now the vertical crosswire of the eyepiece is made to coincide. The vertical crosswire of the eyepiece is made to coincide with each of the two images and the reading is noted. Right? The difference between these two readings gives you D1. The difference between these two readings gives D1. Fine, do you get this? That is the distance between the two diminished images of the slit. Now, repeat the experiment. Now the convex lens is moved towards the biprism. Same experiment, but now the only thing is I'm going to move the convex lens towards the biprism. The convex lens is moved towards the biprism. The convex lens is moved towards the biprism and placed in such a way that the two sharp magnified images of the slit are seen. Right? Once you've done this, again by using the micrometer eyepiece, by using the micrometer eyepiece, the distance D2 between the two images is measured. The distance D2 between the two images is measured. Right? Once you have this, then I can say that the distance between the two virtual images can then be calculated by the formula. The distance between the two virtual images can be calculated by d is equal to square root of d1 into d2, right? Question. So how do you know that d is equal to d1 into d2? I'll just prove this to you. Now in the two adjustments, described above, in the two adjustments described above, the object and the image distance get interchanged. The object and image distances get interchanged by property of conjugate foci. Right? That means if x and y are the object and the image distances, if x and y are object and image distances, right, then in the first adjustment, I can say that size of the image upon size of object is equal to distance of the image upon distance of the object. Distance of image upon distance of object. Right? In which case size of the image in the first case was d1, size of the object was d, distance of the image was y, distance of the object was x. Right? Now that was in the first adjustment. In the second adjustment, again in the second adjustment I can say that same formula if I use, size of the image, that is d2, upon size of the object, d, is distance of the image, x, upon distance of the object, y. Right? Call this as equation 1, call this as equation 2. You can say multiplying equation 1 and 2. Multiply equation 1 and 2. If I multiply equation 1 and 2, I'll get d1 upon d into d upon d2 is x upon 1, y upon x into x upon y. Therefore, I can say d1 upon d into d upon d2 d1 upon d into d2 upon d. d1 upon d into d2 upon d is equal to 1. So I'll get d1 d2 is equal to d square. Therefore, d is square root of d1 into d2. That's how you have measurement of d done. Right? Now once I have this, I can say but fringe width x is equal to lambda d by d. I can say that wavelength, I can find out the wavelength of light. Either way, doesn't make a difference. Wavelength lambda is equal to x d by d. So in that case, I can say wavelength is x square root of d1 d2 by d. That's how you can find out the wavelength of light, right? So this was interference. Now let us see another concept of light which is called as diffraction of light. Right? Now let's move on to rectilinear propagation of light. Now as per the theory of rectilinear propagation of light, light always travels in a straight line, right? See, according to rectilinear propagation of light, light always travels in a straight line, right? But careful observation has shown that light has a tendency to bend round the corners of small obstacles or near slits in their path. Ideally, light should be traveling in a straight line, but if there's a small slit, the light instead of traveling in a straight line would bend. Similarly, if there are corners, if there's an object or small object with corners, the light instead of traveling in a straight line would bend, right? So I can say that careful observations have show that light has a tendency to bend round the corners, of small obstacles or near slits in their path, right? So instead of traveling in a straight line, if there is a small obstacle or if there is a slit through which it has to travel, instead of traveling straight, it is going to bend a little. Fine, do we get this thing clear? And this bending or deviation of light depends upon the dimension of the obstacle and the size of the wavelength. This bending, how much will it bend, depends on A, it depends upon the dimension of the obstacle, B, it also depends upon the size of wavelength, right? So this bending or deviation is small if the dimensions of the obstacle are large. The effect produced is pronounced if the size of the wavelength and the dimensions are comparable. Generally you don't see the bending. But if the dimensions are small and the wavelength is also small, then you can actually see the bending of light as it passes through small obstacles or slit. And this phenomenon of bending of light as it passes through small obstacles or slits is called as diffraction of light. Right? Do we understand what is diffraction of light? I can say that bending is small if the dimensions of obstacle are large, as compared to wavelength, but if the dimensions of the obstacle and wavelength are comparable, then the bending is more pronounced. And this phenomenon of bending is called as diffraction, right? This phenomenon of bending is known as diffraction. Fine, do we get this thing here? So I would have, right? So thus I can say the phenomenon of bending of light round the edges of small obstacle or narrow slits whose sizes are comparable to the wavelength of light and hence they encroach the geometrical shadow is called as diffraction. Since they are going to bend, they are going to encroach the geometrical shadow. See guys, suppose if I had a slit like this, right? I have a source of light. Now ideally, the source of light should travel in a straight line like this, rectilinear propagation of light. On the screen, I would have an image that would be formed. This would be the image that would be formed here and here, up till here, right? So if this is AB, this would be its image A bar and B bar, and this part from, this is say XY is the screen, this part would be the geometrical shadow, and this part up here would also be the geometrical shadow, right? So you would have geometrical shadow on either sides. Now, because of bending, because of the phenomena of bending, suppose if AB is, if a narrow slit AB is placed in a source of light S, right? Then A bar, B bar is the illuminated part of the screen. A bar X and B bar Y are the geometrical shadow. Now, AB is the obstacle of the geometrical shadow, right? Now, ideally, because of bending, what would happen is this ray of light would bend outwards and would encroach the geometrical shadow, right? Because if the size of the slit and the wavelength are comparable, then the ray of light, instead of traveling straight, would bend and would encroach the geometrical shadow, right? Do we get this thing here? The ray of light, instead of traveling in a straight line, if the slit is small, see, I'll show to you in another diagram. Same slit AB. That is how ideally it should have traveled. Source of light. The ray of light should ideally move this way. From here, it should ideally move this way on the screen, and this should give me A bar, B bar, right? Whereas this should be my geometrical shadow. X and Y, this is X, this is Y. But the ray of light, instead of traveling straight, is going to bend a little. It is going to bend a little. Since it is going to bend a little, it is going to encroach the geometrical shadow. This phenomenon of bending of light instead of traveling in a straight line is called as diffraction of light.
So why does it bend?
That's the phenomenon of light. It's an inherent property. When the wavelength and the size of the slit are comparable, then the ray of light, instead of traveling straight, bends, and that phenomenon is called as diffraction. Fine, do you get this thing here? So I can say definition wise, how do I define diffraction? Definition: the phenomena of bending of light, the phenomena of bending of light round the edges of small obstacles or narrow slits whose sizes are comparable to the wavelength, of light, and hence it encroaches the geometrical shadow hence it encroaches the geometrical shadow of the obstacle is known as diffraction. So diffraction is the phenomenon of bending of light. In short, I can say phenomenon of bending of light around sharp corners and edges is known as diffraction. Fine, do we get this thing here? So do we understand what is diffraction? Next, let's see what are the different types of diffraction. Let's understand the different types of diffraction. There are two different types of diffraction. One is called as Fresnel's diffraction. The first kind of diffraction that you have is Fresnel's diffraction. Now, in case of Fresnel's diffraction, the incident wavefront are spherical or cylindrical. In simple language, I would say that the source of light is at a finite distance from the obstacle and the screen. The source for Fresnel's diffraction to take place, the source of light is at finite distance from the obstacle and the screen, on which diffraction pattern is to be observed. On which diffraction pattern is to be observed. Right? That's the first condition for Fresnel's diffraction. Right? Now, the light after diffraction appears to converge towards the screen, and hence no lens is required in the case of Fresnel's diffraction. Light after diffraction, in the case of Fresnel's diffraction appears converging towards the screen, hence no lens is required. No lens is required to observe it. Right? Now, in the case of, so this is your Fresnel's diffraction. In Fresnel's diffraction, after passing through the narrow slit, instead of converging outside, it will converge inward. Right? Hence, the size of the geometrical shadow will increase. That is called as Fresnel's diffraction. This kind of diffraction takes place when the source of light is at finite distance from the obstacle and screen. Right? So, if the source of light is at finite distance from the obstacle and screen, the ray of light after passing through the slit, instead of converging outward, converges inward, and the size of the geometrical shadow increases. Fine, do we get this thing clear? The next kind of diffraction that you have is Fraunhofer's refraction. Fresnel's diffraction, type of diffraction. Now, in the case of Fraunhofer's diffraction, both the that is the source and the screen are at very large distance from the obstacle. Source and screen are at very large distance from the obstacle. Right? So as a result of which the ray of light after passing through the slit diverges. As it diverges, in order to observe the diffraction pattern, a converging lens is required to see this. So I can say a converging lens is required to observe this. Right? So do you understand what are the different types of diffraction? Now, let us see how do we produce a diffraction pattern in a lab. Let's see experimentally how to produce a diffraction pattern. Now, if I were to consider a parallel beam of monochromatic light, it would appear normally incident on a slit. It would appear that it is going to pass straight. But as per the laws of optics, if the beam of light is coming out from a slit, it should be directly perpendicular to the screen, but it is not directly perpendicular. It bends slightly because of diffraction, right? And that's how the diffraction pattern is observed. Now, as it bends, the point where it reaches, it causes maximum intensity. And then in the adjoining places, the intensity goes on decreasing. I'll show you this with the help of an experiment. See this. Let's consider that I have a lens here. You have a point source, right? So ray of light moves out from here, moves out from here, and this refraction, refraction, refraction. So here you have a plane wavefront. This is the plane wavefront. Let us keep a slit. Let's assume that the plane wavefront passes through a slit. It passes through a slit which has sharp edges. Right, it is passing through a slit which has sharp edges. Right, this is my plane wavefront. This is my source of light. This is your lens L1. Right, now let's assume that this distance of the plane wavefront is A. Okay, now as it passes through the slit AC, AC is the center. Let's assume that it passes through the slit AB, where C is the center of the slit. Due to diffraction, ideally it should have passed straight. If it would have passed straight, then this would have been how it would have passed. It will pass straight. If I keep another lens here, it would converge through this lens and would form a point image. That's how the plane wavefront should have passed. This should have been the passing of the plane wavefront, and I should get this image on the screen at point O. But due to diffraction, instead of passing straight, it is going to pass at an angle of theta. It is going to pass at an angle of theta. And this is perpendicular here. So here, instead of passing straight, I am going to get an image that will be right. The rays of light, after passing through the lens, would converge and meet at a point. Right? They would meet at a point, say P on the screen. And do you get this idea? Let's assume that this is lens L2. Right? So now do you understand diffraction? So I can show you diffraction clearly. Here, instead of having the point at O, you will get your point at P. Right? Let's write this experimental setup. Let's consider this. So you will say consider a monochromatic source of light let us consider a monochromatic source of light placed at principal focus of a convex lens L1. Placed at principal focus of convex lens L1, right? Now, and illuminating a narrow slit AB. illuminating a narrow slit AB. Right? Now, due to length L1, the parallel beam of light, that is the plane wavefront, will be incident due to the lens L1. A plane wavefront will be incident. A plane wavefront will be incident on slit AB. Right? Now, once this is done, then you will see a diffraction pattern on the screen. Right? The diffraction pattern is produced on the screen. There you can see, instead of having a point right in the center, you will have a point which will be, instead of at O, you will have a point at P, you will have a bright point at P. Then you will have more diffraction taking place. You will have a point that will be further away from P at Q. But what will be the difference between these points? The point at O will have maximum brightness. That is the point that does not undergo diffraction. The point at P will have intensity which will be less than what is at point O. So as the diffraction pattern moves away from the center, the intensity of light that is going to be produced at that point is going to go on decreasing. So just like interference pattern, you will have a diffraction pattern. I've shown you with one angle theta, you can have with multiple angles, and you will have multiple points that will be formed on either side. But the difference is that the centermost point will be the brightest, and the points on either side will have less intensity. Fine, will you get this thing clear? So I can say that the diffraction pattern consists of central bright band with alternate bright and dark bands. And less bright bands. On both sides. Right? See, if this is the screen, I can show you this with the help of a figure. If this is the screen, this is the central line. This will have maximum intensity. This will be the intensity at this point. On either side, you will have a dark band. This is your dark point. Then again, you will have intensity that will be less on either side. Right? Then again, you will have another pattern with less intensity. So let's assume that this goes up till here. Right? So that is how the diffraction pattern will be. This wavelength here shows maximum intensity. This is central band which will have maximum intensity. Right, which is at point O. Right, now the dark band is going to be formed at lambda by 8 on either side. The next dark band is going to be formed at 2 lambda by 8 on either side, and so on and so forth. The next dark band will be at 3 lambda by 8. So you will have alternate dark and bright bands, and the intensity of bright bands will go on decreasing. This is going to be my first maximum on both the sides. This is my first maximum, Then similarly you will have second maximum, third maximum and so on. This is going to be my second maximum. This is also my second maximum. Here you can see that from the length of the wave you can see that the intensity goes on decreasing, right? The central bright band is called as the central maximum band. The dark and the less bright bands on either side of the central bands are known as secondary maxima and secondary minima, right? The intensity is not uniform over the entire central maximum. It is maximum at a point and it decreases on either side of that point. So it is maximum at point O, and as you go on moving away, it goes on decreasing, right? Do we understand this? So do we understand what kind of diffraction pattern you will get? You will have bright and then the intensity will go on reducing. Yes?
So what is the secondary minima?
You will have the dark and the less bright bands on either side of the central maxima are called as secondary minima and secondary maxima. So this is going to be your first maxima is secondary maxima, secondary minima, right? And then so those are your secondary maxima and minima. Fine, do we get this thing clear? Now this leads us to another concept. Diffraction leads us to another concept. Right? Now it leads us to a criteria called as Rayling's criteria. Now understand this, guys. Your central band, central point is bright and then the brightness goes on decreasing, and as it goes on decreasing you have dark bands that are going to be formed, right? So that means if I were to see a top view, guys, if I were to see a top view of this, first I'll show you a top view of this. You would have a central bright band, then there would be a narrow dark band around it, then there would be a bright band around it with less intensity, then there would be a dark band around it, and then again bright band. Now see, this would have been your dark band, this would be a dark band, there would be a dark ring, so there would be central maximum bright band, then there would be dark band, then again there would be a dark band here. That would be my top view of this, right? And the brightness here, this is my first maxima, would be less than the central maxima. So the top view of this is going to be this way. Fine, do you understand this? Now, this leads us to another concept called as Rayling's criteria. Now, in the case of optical instruments such as microscope, telescope, which are designed using geometrical optics, according to geometrical optics, the image of a point object is produced by an optical object should be a point object, but this in practice does not happen because of diffraction. If I have a point object, its image by rectilinear propagation should be a point object. If I apply geometric optics to it, it should be a point object, but geometric optics is not applied because of diffraction. Hence, the image of a point object will not be a point object, right? It will be nothing but a circular patch with a bright disk at the center surrounded by alternate dark and bright rings of decreasing intensities. Do you understand this? And this is due to the phenomenon of diffraction, and this kind of pattern that you get are called as airy disks. Right? Now you understand why it is necessary to study diffraction, because in the case of optical instruments, when you design the optical instruments, you are going to design the optical instruments assuming that they are going to follow the principle of geometric optics, but they do not follow the principle of geometric optics. Fine? See, I can say that optical instruments are designed by using laws of geometric optics, right? right? According to these laws, the image of a point should be a point, right? So I can say that according to laws of geometric optics, according to laws of geometric optics, according to laws of geometric optics, the image of a point object should be a point. The image of a point object should be a point, right? But in practice, the image of a geometrical point, the image of a geometrical point is produced by the lens is a circular patch, of light with bright disk at the center, with bright disk at the center, surrounded by alternate dark and bright rings of decreasing intensity, right? Why does this phenomenon take place? This phenomenon takes place due to diffraction. This phenomenon of diffraction of light, is called airy disks. So instead of a point image, I get a airy disk, right? Now, what is the disadvantage of this? Suppose if I have 2 point images lying close to each other, both of them would produce airy disks. Since the 2 point images are close to each other, the 2 airy disks would overlap each other. And since the 2 airy disks would overlap each other, the object would appear like a single big object instead of appearing as 2 different small objects, right? I can say therefore, if 2 bright objects are lying close to each other, then lying close to each other and seen through optical instruments some optical instrument, they may not appear as 2 separate distinct objects. They may not appear as 2 separate distinct objects, right? Why? because of the overlapping of diffraction patterns, making their identification difficult. Because of the overlapping of diffraction patterns. Right? Do you understand this? So instead of appearing as two separate objects, they will appear as a single object. Right? So therefore I can say that the two objects will be, now the two objects which are very close to each other are said to be resolved if they appear as two objects through the optical instrument. Two objects which are placed close to each other, because of the presence of the airy disk and the two airy disks will overlap each other. Instead of appearing as two objects, they will appear as single objects. But I still want them to appear as two separate objects. So two objects lying close to one another, if they appear as two objects, then we say that the objects have been resolved. Right? Let's write this down. Two objects lying very close to each other are said to be resolved if they are seen as two separate objects. If they are seen as two separate objects through an optical instrument. Right? And this ability of an optical instrument to produce two separate images of two objects lying very close to each other is called as the resolving power of an optical instrument. Right? This gives rise to the definition of resolving power. What do you mean by resolving power of an optical instrument? Resolving power of an optical instrument, the ability of an optical instrument to produce two separate images of two objects lying close together. The ability of an optical instrument to produce two separate images of two objects lying close to each other is called the resolving power of the optical instrument. Right? Now once I know the resolving power, then I can say that the smallest separation between 2 point objects which may appear just separated is called as the limit of resolution. The optical instrument can resolve two objects. The optical instrument can show 2 point images so long as they are at certain distance from each other. When they come very close to each other, then the optical instrument will not be able to resolve them. The minimum distance that they should be kept at from each other so that the optical instrument resolves them as two separate images is called as limit of resolution. What is limit of resolution, guys? It is the minimum distance at which the two objects should be placed so that the optical instrument can resolve them as two separate images. Right? So it gives rise to another definition called as limit of resolution. What do you understand by limit of resolution? The smallest separation between 2 point objects the smallest separation between 2 point objects at which they appear at which they appear just separated is called as the limit of resolution. Limit of resolution is called as the limit of resolution of the optical instrument. Right, from this what we understand is that the limit of resolution is nothing but the reciprocal of the resolving power. Right, I can say the limit of resolution is the reciprocal of the resolving power right. So do you understand what is the limit of resolution of optical instrument? Fine, do we understand this? And why we have this problem? Because the point image, the point object does not appear as point image, but it appears as airy disk, right? Now that we know what is resolving power and limit of resolution, let us try to define the resolving power of a microscope. Now we have already said what is resolving power of an instrument. Resolving power of an instrument is the ability of the optical instrument to produce two separate images of two objects lying close to each other. So I can say that the resolving power of a microscope is defined as the reciprocal of the minimum distance of separation. We also said that limit of resolution is reciprocal of resolving power. So I can say that resolving power is the reciprocal of the minimum distance of separation between 2 point objects which can be seen as two separate point objects. If I have 2 point objects and if I see them through the microscope and I see them as 2 point objects, then that minimum distance, reciprocal of that minimum distance would be called as the resolving power of the simple microscope or resolving power of the microscope. I can say that resolving power of the microscope is defined as the reciprocal of the minimum distance of separation between 2 point objects for which they can be seen as two separate points. Which they can be seen as two separate points. Right? Do you get this thing here? Now, let's try to get this microscope objective. Let's assume that this is the objective, right? You have the object that is placed over here, right? Light falls on the object. This is light falling on the object. You see this microscope in your lab, right? Light falls on the object and is reflected onto the objective. This is my objective. And then you view it through your eyepiece, right? Let us assume that this is the line of center and this angle is theta, right? So let us assume that lambda is the wavelength of light, lambda is the wavelength of light used to illuminate is the wavelength of light used to illuminate 2-point objects placed in the medium of refractive index. Medium of refractive index mu, and theta is the semi-vertical angle. Theta is the semi-vertical angle of the cone of light entering the objective. Cone of light entering the objective. Fine, we get this thing here. So in which case I can say that according to limit of resolution, what is limit of resolution? It is the minimum distance of separation between 2-point objects. So there was a scientist by the name Abbe, right? So according to physicist Abbe, I can say that the minimum distance at which the two objects can be placed is lambda upon 2n sine theta. The minimum distance at which the two objects can be placed is going to be wavelength of light divided by 2n sine theta, where dx is the minimum distance of separation between 2 points. Minimum distance of separation between 2 points, right? N sine theta is defined as the numerical aperture of the objective. Numerical aperture of the objective, right? In that case, we had said that resolving power is the reciprocal of limit of resolution. Therefore, I can say that resolving power is the reciprocal of limit of resolution. That means resolving power will be 2n sine theta upon lambda. Thus, smaller the value of dx, greater will be the value of the resolving power. That means from this what we understand is that the resolving power of the microscope depends upon resolving power of microscope depends upon, what are the factors it depends upon? One, it depends upon the wavelength of light, right? Second, it depends upon the refractive index. It depends upon the refractive index n. This is wavelength. It depends upon the refractive index n, right? And third, it depends upon the semi-vertical angle of the cone, theta. Semi-vertical angle of the cone. Right? These are the factors on which it depends upon. Right? So if I want to increase the resolving power of my microscope, how would I increase the resolving power of the microscope? It is directly proportional to the refractive index. It is directly proportional to the semi-vertical angle and is inversely proportional to the wavelength of light. So if I want to increase the resolving power of the microscope, I cannot change the refractive index. So either I change the semi-vertical angle by changing the numerical aperture of the objective, or I decrease the wavelength of light used for illuminating the object. By using either one of them, I can increase the resolving power of the microscope, right? Okay, we'll stop this here for the day. Thank you very much.